So, Vanakkam. So, we will continue our lecture. So, we have been discussing about the estimation of the time domain parameters, particularly the duration which is responsible for damage of the structures. So, we have seen that higher amplitude, lesser duration may not cause a damage, but lesser amplitude, longer duration may cause a damage. So, the understanding durations are very important. Then scientists start working at finding out the duration. So, the duration is basically the time interval of the accelerometric signal in which the seismic motion is significant. Okay, so, that is what it is a duration. Several definitions of the durations are available based on the parameter used to classify them. Most frequently used durations are we are going to discuss in our class. So, that is like bracketed duration, uniform duration, significant duration, effective duration and effective shaking duration. So, these are all the durations which is most widely used for in the engineering practice. So, what is mean by the bracketed duration? So, bracketed duration is actually the time total time elapsed between the first and last exceedance of the specific level of acceleration. In generally the threshold acceleration value is taken into 0.05. So, if you plot your acceleration versus time history of the particular ground motion, even though you record sometime velocity and you convert it to the acceleration by differentiation, then that acceleration time history you have to identify what is the first 0.05 g, which may be the positive or negative. Okay. So, you can draw a line which is like 0.05 and minus 0.05 like this. Then you can see which is the first signal which is crossing. Okay. So, that point you can consider as your starting point of the bracketed duration. Then you can see where it ends, basically it ends at this place. So, this will be considered as a end point of the bracketed duration. So, the bracketed duration is basically this minus this. Okay. So, that is called as a bracketed duration. So, this 0.5 okay, so is considered as a bracketed duration quantity. The bracketed duration interval between the 2 points in the time where the acceleration amplitude first and last exceedance prescribed level of point this one, but this was later. Okay. So, has been Bolt it was suggested by this in 1969. Later the Ambrasi and Sharma said that, so instead of 0.05 one should go for the 0.03. So, that means the same bracketed duration you can define for the 0.05 as well as 0.03. So, depends on that your duration changes. This is called as a bracketed duration. So, the next one is a uniform duration. The sum of the time interval during which the acceleration greater than the threshold level is called as a uniform duration. So, that threshold value is left to the user. You can define whatever threshold value. Basically, you plot acceleration versus time history, the absolute values. Only consider the interval for which the ground acceleration above the threshold value. For example, you define this as a threshold value, then the time T1, T2, T3, T4, T5 wherever it exceed. So, that summation of this is actually the uniform duration of the ground motion. Okay. So, this you can see the summation of the time interval exceeding the threshold value definition. So, this threshold value you can define as per your choice. Okay. So, before going to other duration, we will try to understand the areas intensity. So, the areas intensity IA is the measure of the strength of the ground motion. It determined the intensity of shaking by measure the acceleration and transit seismic waves. Okay. So, areas intensity, even though the intensity term comes, but it was invented by the scientist Arias, which is not similar to your modified Mercalli intensity or any other intensity, which is not similar to other intensity scale which you are used. This is the intensity which basically shows the strength of the ground motion and determined from the recorded acceleration data or recorded earthquake data. So, it is a measure of the strength of ground motion. If the larger the area's intensity, stronger is the earthquake. It has been found that fairly reliable parameter to describe earthquake shaking necessary to trigger landslide. It was proposed by the Chilean engineer Astro Arias in 1970. It defined the time interval of the square of the ground acceleration is called as a Arias intensity. Arias intensity could be alternatively defined as the sum of the all the squared acceleration values from the seismic strong motion record. So, you can see that the Arias intensity equal to basically the time integral of the square of the ground acceleration given by this one. So, this is the Arias intensity, the square integral 0 to Td. At is acceleration in meter per second square, t in time in second, g is the acceleration due to the gravity, Td is the duration of the signal above the threshold value. So, you can define a threshold value. For example, generally for the structure requirement they take 0.01 as a threshold value g. So, theoretically the integral should be infinite. So, the Euclid plot is the time history of the normalized Arias intensity. The Arias intensity expressed as a percentage of the total Arias intensity and as represented as a normalized variable is called as a Euclid plot. So, the Euclid plot is basically you estimate Arias intensity, you normalize with the maximum value, you define with the maximum value, then you get another plot. That plot is called as a Euclid plot. This is the typical Euclid plot of the Somali earthquake, where you can see where it starts and ends, you have the different percentage. So, this data is being further used for estimating the duration. That duration is basically called as a significant duration. Okay. So, the significant duration is based on the accumulation of the energy in the acceleration represented by the integral of the square ground acceleration velocity or displacement in the Euclid plot. So, it is the interval over which some portion of the total integral is accumulated. For example, the most commonly used interval is 5 to 95% or 5 to 75% of the Arias intensity Euclid plot. So, if you take the Euclid plot, you can see, so here you know what is the 5%, 20%, 10% like this, you draw a horizontal line on 5%, horizontal line on the 95%, then you can define a significant duration for that particular period. So, a significant duration dA for 9 to 95% is that value. Similarly, if you want to define a 5 to 75%, then you can draw a line. So, this duration is called as a significant duration 5 to 75% Arias intensity Euclid plot. Okay. So, the significant duration basically you can see the typical significant duration of the your typical earthquake. So, this one basically gives 5 to 75%, this one will give the 5 to 95%. So, where the 95% of the structure energy starting here, it is the energy where 95% reached, 5% starting here, 95% reached, then reaching to 100% where the structure will collapse. So, this period is considered as a significant duration of the earthquake. So, this is the typical earthquake where you can see how the bracketed duration and significant duration is. So, here you can see that the bracketed duration is 19.4 seconds. The same earthquake, the significant duration is 15 seconds. So, here you are observing directly your peak ground acceleration and then taking 0.05 g. So, here the 5 to 95% energy from the Euclid plot, which is obtained from the integral of the acceleration square. Okay. That is the difference between these two. So, the next acceleration is called as a effective acceleration. So, the effective duration or effective duration is actually is the function of the time interval between the T0 and Tf, which mark beginning and end of the strong shaking phase defined by the absolute criteria. So, you define your absolute criteria in the form of Arias intensity, then so the time between the T0 and then the Tf, that period is called as a effective duration. So, generally it is absolute intensity is basically they take respective the 0.1 meter per second. Okay. So, then this is the value where 0.125 meter per second. So, you can see this period is the effective duration. So, the effective shaking duration, the effective shaking duration is the time interval between the first and last amplitude by considering the value of 0.01 g, 0.01 g. Then the accumulated energy of the three component proceed the effective shaking duration EDS for time window which is less than, which has 5 to 95% of the total energy within amplitude of threshold. This definition considers the major energy part of the part of amplitude 0.01 g. So, this effective shaking duration has been recently defined based on the Japan earthquake data. So, where they try to see that this significant and effective duration giving a different values, and again you are getting another values called as effective duration. So, in order to attain a uniform level, they introduce the effective shaking duration which takes OSID flat into consideration and also acceleration into consideration and gives the new definition. So, this is actually the bottom panel the presents the cumulative energy which the time a particular ground motion used in the study. You can see here the significant duration is from starting to year, and then the effective shaking occurs generally from year to year, where you can see the threshold value of acceleration is exceeding. Okay. So, the blue line marks the time window of the acceleration which is 0.01 g, okay, and above. So, the red line marks the time window of the accumulated energy for the 9 to 95%. So, it can be seen that the significant duration is less than the acceleration which causes a damage. So, then they come up with the definition of this effective shaking duration which is more than the significant duration. Okay. So, more than the your 9 to 95% OSID flat duration, but it is less than the significant duration. So, this damage is caused more on this portion. So, this effective shaking duration of this is need to be considered in the design. That is what the new definition it is given to for the this duration estimation. So, this duration, okay, so there are we have discussed about the 5 type of duration. So, this duration basically important to describe how much time it takes the structure to fail in one angle. Second, how much energy the signal carries. Third, how the seismic wave generated at a source reaching to your site. So, these are all the information included in the duration estimation. Okay. So, this duration estimation basically can be found as a total duration. So, the total duration is basically Ts plus Tp. The Ts is basically denoted as the source duration. The second term Tp denotes a path duration. The source duration is given as a inverse of the corner frequency. The equal acceleration greater durations are generally damaging. So, the equal energy shorter duration presents a greater hazard. So, these total durations are generally used for the simulation purpose of the ground motion. So, if you want to simulate synthetically the earthquake signal which generally you record for the earthquake which does not have the recorded data. So, that time you need to know what is the total duration, source duration, path duration. There are studies people carry out on how the source duration, path duration varies at one place apart from the duration what we discussed in the so far. So, this duration basically gives idea about how much the energy carried by the earthquake waves, okay, how it basically dissipated, how strong it is, okay, in the structural system. So, that the longer duration earthquake basically causes a more damage than the shorter duration earthquake with the same amplitude. Okay. So, these 4 durations are there. So, these durations also as we discussed in the intensity. So, these durations also need to be estimated, and this duration there are equation for duration prediction model. Okay. So, as you know that this duration is controlled, okay, by the a particular location area. So, for example, in this is the ground. So, earthquake occurs somewhere. So, the waves are reaching like this, then you have the several layers. So, it reached this place. Okay. So, when it reached this place, basically it goes to the station where it recorded. Okay, it's where it recorded, it goes actually. So, when it recorded goes like this. So, I can make this as a horizontal plot so that it is easy for to understand. So, this is the ground. Okay. So, this is the rupture. So, this is the rupture point. Okay. So, then the waves are generated. These waves are travel like this, then you will have the different material. Okay. Then these waves are basically undergo this layer. So, you will have the basically station here which record a earthquake. Okay. So, this is basically below the this basically a ground level. So, this basically ground level. Okay, ground level, this reaches. So, this is basically a source. Okay, this is the path, this is the site. Okay. So, this wave starts from here and goes here and is going. So, this data only you are seeing as a like this. Like this you are seeing this. So, this will be the acceleration or velocity and this will be the time. So, we have noticed that the durations are defined is the function of your acceleration values or is the square of acceleration. Acceleration means you can take 0.3 g or 0.505 g where it crosses. Okay. Or you can take Osid plot where you will integrate a acceleration square and it gives a 5% to 95% energy, or is sometimes the uniform mass aspect where 0.1 g or 0.01 g taken into account. You can see that this waves when is starting from this place travels like this and reaches. So, this is generally roughly about 10 kilometer from the site. The depth 10 kilometer. So, this station depends upon the station. So, this will be like traveling on the material where you have the rock which has a 2000 meter per second velocity, and this will be the rock which 1000 meter per second velocity, 700 meter per second velocity. This will be 150 200 meter per second. You can see that this is actually a 2.5, okay, so kilometer per second, correct, same thing. So, here it will be 200. So, 2500, you can see that about 10 times, okay, so more than 10 times it is lower than this. Because of this, the wave which what you can see here are completely different from here. Okay. So, if you have the facility, if you have the seismic record at a bedrock at different level, you can understand how this wave duration and amplitude influenced by the local geology. So, generally the durations, okay, so will change because of the several layering system. Okay, the source duration and the path duration will change due to the site condition. Okay. So, that duration factors are very important, which is very specific to particular location. So, as you have seen that each earthquake you can estimate what is the significant duration for a 5 to 95%. I am giving the example, and one value for given M and R. Okay, this is the M is earthquake, R is basically your distance. So, like this you can accumulate several data. Okay, then you can also, as I told you, that intensity predictive equation, similar to that one can also generate a duration predictive equation. That means you can have the equations which can be used to find out a duration of the earthquake. So, is the duration of the, like for example, D is the function of your M, R and site. Okay. So, if you have the large number of data, so this will be like a empirical formula which we have seen, okay, is the like A plus B M plus C M R, okay, power D, something like that. You can get a multi-regression analysis where the magnitude of earthquake, R of the earthquake, site can be taken into factor. That kind of equations will be useful to identify what is the duration you can expected in the region. Because if you have one record, you will get only the one duration estimator. So, if you have the large number of record in the region, you can know that how much these durations are, varies, what is the standard deviation. This kind of functional data are functional form, okay, which is called as a duration predictive equation, will be used to estimate what is the duration you can expect for the given magnitude and distance at a particular location for the rock site as well as the soil site. So, these are all the very important parameter to design. It is not only you get the ground motion parameters, which is like acceleration, that is also there is a equation to predict a peak ground acceleration. So, then similarly there is a equation to predict a peak ground duration, peak duration or significant duration, function from the significant, effective or uniform, whatever they might be described. So, this kind of development happened in the last 15-20 years. So, where people thought that it is not the only the matter of amplitude, it is also duration of the earthquake has to be considered, particularly when you want to assess a landslide, liquefaction and even a damage potential. So, as on India, there is not much study has been done on duration predictive equation. So, we have started some work where we have done collected several data and try to estimate a duration of the different earthquake and try to develop a duration predictive equation. So, we have success so far duration predictive equation for peninsular India, because we collected data from the many stable continent region and then try to estimate a effective duration and significant duration and try to arrive a duration prediction model for the intraplate region, which considers the Northeast America and then the Australia and some earthquake in the southern India. So, using that we have done, that is the first and unique work on duration prediction equation for intraplate region, which is published in the Journal of Seismology. So, as I said that I also do research on these areas whatever I teach. If you want to refer that paper, you can refer. So, similarly for the similar kind of equation needed for the Himalayan region, right now we have done the analysis, but we yet to publish. So, we also found that in the same earthquake, wherever you have the longer duration, you have the higher intensity of damage. That is what we studied. If the durations are more, the energy accumulated or energy transferred to the structure is very stronger. That will result in more damage than the regular normal or short duration earthquake. So, this duration has to be estimated by considering the data recorded in the region. Then you can use that many duration record to fit develop a duration prediction model. Okay. So, this we will discuss further in when we are talking about the prediction models in engineering seismology in later scale. So, right now there is no such kind of duration model developed based on the Himalayan region data as on now. Okay. But there are models which predict as the function of your peak ground velocity or peak horizontal acceleration. There are many couple of models are there which is available for southern India as well as the North Indian region, where you have the ground motion GMP, which is called as a ground motion predictive equation. So this GMP basically y, okay, so you can term y, then which will be the function of again your m, r and site s. So m is a magnitude, r is a. So as we said that we get a PGA from particular earthquake record. So that is actually known for the given m and r. So similarly you get several PGA, then you plot the data versus like PGA versus your distance for the given magnitude. Okay, then you can do a multiple regression analysis is the function of m and r and site condition. That equation is called as a GMP or ground motion predictive equation. So from the parameters what we have seen that, so you can estimate the time domain parameters as a peak values, peak velocity, peak acceleration, peak displacement, and then duration values, which is the function of basically your how many cycles repeat in the record, and as well as your strength of or energy of earthquake. So that you can, so using these two you can get a predictive models. So these predictive models basically help you to arrive your future what is the expected value for the unknown magnitude and distance. So that is what it can do. So right now we are interpreted a data direct record of the earthquake. We are not done any processing or any conversion of the data. Simply we have taken acceleration time is t record. Okay, then we interpreted the peak value and how many times it repeats. So that details we have used to interpret the time domain parameters. So the next parameter is basically the frequency domain parameters. So the frequency domain parameters means whatever time history data we obtained in the seismometer or accelerometer, that should be converted into the another form. Okay, it will be transformed to the frequency parameters. That parameters, from that you will estimate some parameters. Those parameters is called as a frequency domain parameters. So these frequency domain parameters are important because the source and the path, okay, these are all the function of the frequency of the wave which we have seen. We have seen that the low frequency, intermediate frequency, high frequency component of the wave, which component, which station will record. So these are all related to the seismic moment at a source. So that understanding of the frequency domain parameters will help basically to get your model, okay, ground motion simulation model or synthetic ground motions. Simulation of the ground motions at a particular location is possible using this kind of data. So which will be we are going to discuss in the next class of the frequency domain parameters. So with this we will close today class. Thank you very much. So we will see you in the next class.